Hello, everyone. My name is Benet Harris, and this is my Project One from Idea to Product 5 Keys to Smarter Engineering. The 5 topics I'll be covering today are product lifecycle, design for manufacturing, design for assembly, problem solving process, and prototyping. So let's talk about the product lifecycle or PLC. So, what is a PLC? PLC includes every stage a product experiences from initial design and development through production and distribution to its use and finally its disposal or recycling. And its 5 stages include the product development, market introduction, the growth, the maturation, and the decline. So let's apply this to the real world. Let's take Apple's iPhone. Apple plans yearly iPhone releases to match the growth and maturity cycles. The first iPhone was released in June 2007, just called the iPhone. And the most recent release was in February 2025, which was now the iPhone 16e. So as soon as they hit the decline stage in the life cycle, that's when they come up with their next model. That's when they release their next model. But why is this important? Product lifecycle gives structure to the chaos of product development. It helps with avoid wasting time and money with poor planning, and it helps us to think ahead and support proactive planning. But why does that matter? It's because every product has a life, and without PLC, you risk over designing, underestimating costs, or miss the chance to improve. So the capabilities for PLC are that you can design smarter, optimize production, reduce cost, or improve sustainability. But the limitations include that it's not always predictable, it's market dependent, and it doesn't explain why performance changes. So let's talk about design for manufacturing or DFM. So DFM is the concept that each part or component of a product must be designed to meet all functional requirements while also ensuring that it's manufactured easily and cost effective. So ways to design for manufacturing include changing the section thickness, making sure all your sides are the same thickness and uniform, creating draft angles, making sure your bosses are connected to a wall, um, cornering out the corners so they're not sharp, rounding them out, increasing the number of ribs. So instead of having one thick rib, you have multiple ribs of a thinner distance. So let's take Legos, for example. Legos have a precision design, so they fit perfectly together, have a simple geometry, and they use efficient manufacturing from ABS plastic using fast, repeatable injection molding, and it's also cost effective. And they have minimal waste, so the inside of Legos are hollowed out, so they reduce excess material and support recycling. And you could take a Lego from today and one from 1900s, and it would still fit together perfectly because Lego has maintained its consistency through their designing for manufacturing. But why is that important? It helps bridge the gap between design and production. It reduces the risk of delays and errors. It allows for smarter use of materials and it lays the foundation for a smoother, more scalable process. But why does that matter? Even the best design fails if it can't be built easily or affordably. It directly affects the product's cost, quality, and time to market and helps companies stay competitive. So the capabilities include reducing production costs, improving manufacturability, increasing product quality, minimizing waste. But the limitations include that one size does not fit all. The initial time investment may be great, and you may have a potential aesthetic loss. So let's move to design for assembly or DFA. DFA is about making a product easy and efficient to put together. It focuses on how parts fit and work during assembly, while DFM looks at how parts are made. The goal here is to use fewer parts, make connections simpler, and cut down on assembly time and effort. So, ways to design for assembly include reducing your part count, making sure you have ease of handling, fixing insertion issues, making sure you're selecting the most inexpensive fastening or fasteners, and you eliminate tangling or nestling and eliminate secondary operations such as drilling, screwing, twisting, bending, things like that. But let's really look at it. Let's look at IKEA products such as a bookcase. On the right, you can see that the bookcase, when they're built, the dimensions are like a 15 by 11 by 79, but the package itself is relatively thin because they have a flat pack design. So the parts fit compactly for easy shipping and storage. They have simple assembly. You don't need any special tools. They have fewer unique parts. So a lot of the parts are symmetrical, they're interchangeable to help speed up assembly. And it's also user friendly. The instructions have pictures. It tells you how many of each part you need, how many people you need, what steps to take, and they also pre-drill the holes for you. So I think that IKEA does a great job at designing for assembly. But why is that important? DFA shifts the focus from just designing for function to designing for the real world. It encourages cross functional thinking and pushes us to think early about how a product will actually come together. But why does that matter? Because products don't just exist in theory, they have to be built and they have to be built well. DFA influences the entire life cycle of a product. A great design is useless if it can't be assembled efficiently or consistently. So the capabilities for DFA is that it reduces assembly time, it decreases the part count, it enhances user experience, but the limitations are that it may restrict complex features that you may have wanted to add. It can conflict with other goals you may have had. It requires detailed planning and it's not always suitable for low volume products. So let's move to the problem solving process. The problem solving process is a structured approach that starts with clearly understanding an issue, moving into generating and evaluating possible solutions, and finally deciding on the best course of action to move forward. So let's take into example the Apollo 13. Apollo 13 had a life support system failure where an oxygen tank exploded and the CO2 filters couldn't support all three astronauts. So NASA had to monitor the levels and confirm that yes, they are in danger because the CO2 levels were low. And so the engineers on board used household items like tubing and tape, and they came up with options that a duct tape adapter could work to fix the problem with the CO2. So NASA sent the instructions and the crew built a working CO2 scrubber. So from then on, the focus kind of shifted on reentry and the systems were redesigned for future missions and redesigned for emergency planning and implemented emergency procedures into future steps and spacecrafts because of Apollo 13, because of the problem solving process. But why is that important? The problem solving process, it helps us approach challenges with purpose. It brings structure and confidence to uncertainty, and it turns our trial and error into a thoughtful process. But why does that matter? Problems are constant. What changes is how we handle them. A good process prevents us from jumping to conclusions, and it helps our team move forward when we're stuck. But also, the problem solving process is a foundation for innovation. The capabilities of the problem solving process include providing structure and clarity, encouraging critical thinking, improving efficiency, but the limitations that it can be so time consuming and it's not always linear and it relies on information that you have available. Now let's move to prototyping. So, prototyping are physical models of products that are essential tools in design and engineering process. They allow teams to explore, test, and refine product ideas in a hands-on, tangible way. So, there are four types of prototyping. Proof of concept, which focuses on whether the product works, not how it looks. Proof of product is about refining design details. Proof of process is used to check if manufacturing methods and design work together. And proof of production is like a trial run before the actual launch. So let's take the Dyson vacuum. So James Dyson built 5,127 prototypes over 5 years before launching the DC-01 in 1993. He wanted to fix suction loss in traditional vacuums, and why his prototyping was so critical because every prototype he used, he tested different suction methods, different materials, different airflow designs, and his early versions prioritized function over appearance, keeping costs low. And the impact he had, this hands-on approach led to the breakthrough of DC-01 and built the foundation for a multi-billion-dollar company now known for its models like the Dyson Ball, the V-Series, and the robotic vacuums. So his sketches, his prototypes led him to be very successful in the world of engineering. And now he's come so far from the prototypes, he's able to apply what he knows. He's able to innovate. So, but why is prototyping important? It translates our ideas into physical form so that we can test them, we can improve them, and it brings clarity to design decisions by telling us what works and what doesn't. And it encourages like iteration, creativity, and continuous learning. But why does that actually matter? It's because great ideas don't mean much if they don't work in the real world. Prototyping prevents mistakes by catching it early. It helps us move our projects forward when we get stuck. It turns our uncertainty into action. And it's a key step in actually creating products that are functional, usable, and ready for production. So its capabilities include testing and validating ideas early, supporting iterative design, reducing risk, and most of all, demonstrating feasibility. But the limitations are that it can be time consuming. It may not fully represent the final product, it may be costly, it may give you false confidence, and it has a limited scope. So here are the sources that I used throughout this project. And thank you guys for watching.